Industrial filtration systems operated in high-temperature environments face a unique and often underestimated challenge: extreme temperature fluctuations. Whether it's a cement kiln ramping up on a freezing morning or a gasification unit undergoing an emergency shutdown, the rapid shift between ambient and process temperatures can wreak havoc on filtration components. These fluctuations introduce mechanical stress, compromise filter integrity, and can lead to production standstills. For operators, the consequences of ignoring thermodynamics could lead to cracked filters, degraded seals, and rising emissions, which all can threat production targets and regulatory compliance standards. To combat these issues, modern hot gas filtration systems must be engineered with materials and designs that withstand aggressive thermal conditions. Woven wire mesh and ceramic filter elements are increasingly favored for their ability to endure extreme temperatures without warping or cracking. Additionally, implementing controlled heating and cooling protocols, robust installation, and predictive monitoring tools can help to stabilize system performance. These strategies are designed to not only protect the filtration media, but also to extend the lifespan of the entire system, ensuring consistent operations even under extreme conditions. Hot gas filtration systems operate across a wide spectrum of temperatures, each presenting unique challenges and requirements. These systems typically process gas temperatures ranging from 260 degrees Celsius, 500 degrees Fahrenheit, to as high as 1000 degrees Celsius, 1832 degrees Fahrenheit, depending on the industry and application. The surrounding atmospheric conditions, which are often between 0 degrees Celsius and 40 degrees Celsius, 32 to 104 degrees Fahrenheit, create significant thermal differentials that can stress filtration components during startup, shutdown, or surprise system events. Processes such as biomass combustion, industrial drying, and certain waste-to-energy operations typically fall within the 260 to 450 degrees Celsius range, 500 to 840 Fahrenheit. While these temperatures are more moderate compared to extreme applications, the contrast with the ambient air still poses a risk. Systems in this range must be designed to handle gradual heating and cooling cycles to prevent condensation and material fatigue. Filter media like glass fiber or intermediate-grade stainless steel mesh are commonly used here for their balance of thermal resistance and cost-effectiveness. Cement kilns, lime production, and chemical reactors often operate between 450 to 650 degrees Celsius, 840 to 1200 Fahrenheit. At these levels, the risk of thermal shock increases significantly, especially during cold starts or emergency shutdowns. Materials such as woven wire mesh and ceramic filters become essential due to their ability to withstand rapid temperature changes and corrosive gas environments. These filters must also be supported by robust housings and insulation to maintain system integrity. Advanced applications like metallurgical refining, gasification, and pre-SCR polishing push filtration systems into that 650 to 1000 degrees Celsius range, 1200 to 1832 Fahrenheit. At these extremes, even minor exposure to ambient air could cause rapid cooling, leading to cracking, condensation of aggressive compounds, and catastrophic media failure. Ceramic filters made from low-density refractory fibers and alloys are preferred for their thermal shock resistance and cleanability. Woven wire mesh is also great to combat thermal shock. These systems often incorporate heat tracing and predictive monitoring to maintain safe conditions. Hot gas filtration systems are engineered to operate within specific thermal parameters. When these parameters are disrupted by sudden temperature changes, such as cold air ingress during startup or emergency shutdowns, the filtration media and system components can suffer. These fluctuations cause materials to expand and contract at different rates, leading to mechanical stress, seal degradation, and compromised filtration performance. Maintaining temperature stability is not only critical for protecting the filter media, but also for ensuring consistent particulate capture and system reliability. One of the most immediate consequences of thermal instability is a rising pressure drop across the filter media. As temperatures fluctuate, particles can sinter onto the surface of the media, forming hardened layers that resist cleaning. In colder conditions, condensation may occur, creating sticky particle deposits that further restrict flow. These factors increase the differential pressure, forcing fans or blowers to work harder and consume more energy. Over time, this can lead to reduced throughput, higher operational costs, and increased wear on system components. Rapid temperature changes can cause cracking or warping, especially if the filter media lacks sufficient thermal resilience. Even woven wire mesh, while generally more robust, can experience fatigue over repeated thermal cycles. Seals and gaskets are also at risk, as thermal cycling can degrade elastomeric materials, leading to bypass leakage where the filter gas escapes the media. This not only reduces filtration efficiency, but also can result in elevated emissions and downstream equipment fouling. Temperature fluctuations can interfere with cleaning mechanisms like pulse jet systems. If the particles become sintered or wetted due to condensation, standard cleaning cycles may fail to restore baseline pressure drop. This forces the system to trigger more frequent cleaning cleaning sequences, which may not be effective and can accelerate wear on the filter elements. In extreme conditions, cleaning systems may become overwhelmed, leading to persistent fouling and reduced system uptime. So, optimizing cleaning protocols for thermal conditions is essential to maintain long-term filtration efficiency. Choosing the right filtration media is the foundation of thermal durability. Woven wire mesh and advanced ceramic elements are among the most effective materials for resisting thermal shock. These materials maintain structural integrity even when exposed to rapid temperature changes, thanks to their low thermal expansion coefficients and high fracture toughness, offering both chemical inertness and mechanical strength. And beyond media selection, the design of the filtration system plays a major part in mitigating thermal damage. Matching the thermal expansion properties of the filter media and housing materials helps prevent seal failures and weld fatigue. Insulating the vessel and ductwork reduces the risk of cold spots where condensation can occur. In high-risk zones, heat tracing can be applied to maintain temperatures above the dew point, preventing condensation formation and plugging. These design features help maintain a stable thermal environment and reduce the likelihood of mechanical failure. Controlled heating and cooling ramps during startup and shutdowns are essential to avoid abrupt thermal shocks. Operators should avoid introducing cold air slugs or rapidly heating the system without preconditioning. Installing thermocouples at critical points allows for real-time temperature monitoring, while differential pressure sensors help to track media performance. Predictive maintenance tools can alert operators of emerging issues before they escalate, enabling timely interventions that preserve system integrity and uptime. Cleaning protocols must be adapted to account for the effects of temperature on particle behavior. For example, sintered or wetted particle layers may require more aggressive back pulse timing or intensity to dislodge effectively. However, excessive force can damage the filter media, so optimization is key. Routine inspections of filter elements, seals, and housing should be scheduled to detect early signs of thermal fatigue, such as cracking, misalignment, or embrittlement. Proactive maintenance not only extends the life of the system, but also ensures consistent filtration performance under extreme conditions. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things WS Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.